Welcome back again to the lecture series Foundations of Quantum Mechanics. We are picking up where we left last time. So we have, let's see, we first went through this Mermin-type Gedankenexperiment that explains to you, without referencing the Schrödinger equation, what is the essence of Bell's inequalities in terms of logic. And then we took a step back. We went through the Einstein-Podolsky-Rosen paper, and we said that Schrödinger then coined the term entanglement, and we understood that there is a spin version of the original Einstein-Podolsky-Rosen Gedankenexperiment. And now we are at the heart of the first part of the lecture, so to speak, because we will now really dive into Bell's inequalities as Bell introduced them. So that's what John Bell came up with in the 60s. And I want to start right away by explaining again what's the idea behind this. So we are now subchapter 2.3, Bell's inequalities. And the idea is the same basic idea, or the same question that already Einstein-Podolsky-Rosen posed, namely, can we find an underlying microscopic theory to explain at least the outcome of the EPR experiment, and then maybe in the future also all of quantum mechanics? And with an underlying microscopic theory, by that we understand something that would give us more insight, that would, for example, describe in detail maybe the trajectories of particles or something like that. But here it's more modest, and that was the part of the genius of Bell. He said, let's just try to find such an underlying theory for the specific purpose of the EPR experiment. And it is important to understand that the version of the EPR experiment he had in mind was actually the spin version that I explained last time. So basically where you have a source and you have the source emitting particles that have spin, and you will only concentrate on the spin degree of freedom. And you will assume that they are emitted in a very particular spin state, namely a spin singlet state. So that's the state up, down, minus down, up. And we learned last time that this is a very peculiar and special state. It's completely rotationally symmetric. So the way it's written down here, supposedly it's written down on the Z basis. So if you measure spins along the Z axis, they will be up, down, or down, up. But if you were to pick any other quantization axis and pick the same quantization axis for both spins at the same time, you would find exactly the same wave function and exactly the same behavior. So you have the source of spins, and then out here you have spin measurement apparatuses, which might be Stern-Gerlach apparatuses working with an inhomogeneous magnetic field. And then they can detect whether the spin is pointing up or down by deflecting the spin up or down, depending on its spin orientation with respect to a magnetic field. So that's the setup. And then you would find correlations similar to the correlations that EPR proposed. Now, if your goal is to come up with something like a microscopic, maybe classical type theory to explain the results of this experiment, one piece of this theory must certainly be to describe the spin of a particle, and then to describe the measurement of a spin. So we need some description of the spin and some description of the measurement. And then we need this not only for a single spin, but for two spins, and we somehow have to set it up such that the measurement results will be correlated. But let's first talk about a single spin. Now, the microscopic toy model, if you like, that looks a little bit like classical physics that you could cook up for a spin is obviously something as if a particle is maybe rotating around its own axis and the spin is somehow the angular momentum. But in any case, the angular momentum would be represented by a vector. And so the microscopic model must look very much like what we are always drawing here. So we would make a model for a spin where I would say a spin in this model is just a vector, a unit vector that points in some direction. And for the moment, let me call this vector lambda, because that's the notation that makes sense in this field. Otherwise, you might call it S or so. So I can draw the particle, if you like, as a little ball. But what's important is this vector lambda that points into a particular direction. And if it points in another direction, okay, and then that means the spin points in another direction. Now this is very naive, of course. The problem is now the measurement, because you know that if you take this series on the classical level, then the spin vector can really point continuously in any direction. And if you were to measure it, you would measure all the components of the spin vector at the same time, classically, and you would never get the kind of answer that quantum mechanics gives you, which is a discrete outcome. It's binary, it's either up or down. So you choose a measurement axis, and then you get only up or down. So the question is, if I want to perform a measurement of the spin along a particular axis, again represented by a vector, let's call this A, what should happen? What should be the outcome? The outcome should be discrete. And so you have to invent a rule here. The question is not whether the rule is very physically motivated, but at least you have to invent a mathematical formal rule. The outcome should be discrete, it should be binary. So the idea that Bell came up with is in principle very naive. The idea is that if this is your measurement axis direction A, and that is the direction of your spin vector, then you can still generate a discrete binary outcome if you say, well, I get the outcome up if lambda and A point in the same direction, or at least approximately in the same direction. So if this angle that I'm drawing now here is less than 90 degrees. So if you want to formulate it in terms of a scalar product, if the scalar product is positive, so they're pointing more or less in the same direction. And otherwise you get down. So that would be the rule. That at least is plausible. It's certainly a binary outcome. And it will certainly give the expected result in case you measure exactly along the spin direction. Then you should always get up. So that's nice. So if we want to write this down a little bit more formally, we could say the measurement result, I will call this capital A. It depends on both the measurement axis and the spin direction. And it's plus minus 1, up or down, depending on the sign of lambda times A. So I could just say it is the sign of lambda times A. Yeah. So that's a very simplistic model for a spin and the measurement of a spin. No one claims that we know how physically this should work out, but at least it's a possible model. And now you can go ahead. I hope this is clear. Yeah, if there are any questions, it would be important to ask now. Otherwise, I would go on, because now you want two spins, of course, and you want them to be correlated. So what can you do there? Well, we can directly copy our previous drawing. So if, for example, this is the spin vector of the particle that will be measured at site A, then in order to get these anti-correlations that are built into the singlet states, so if one is up, the other has to be down, wouldn't it be the most obvious choice that you say in my toy model, the spin vectors are always anti-parallel? I mean, you can do that. You could take lambda random overall. So the direction of lambda is different for each pair of particles that is emitted by the source. But the two particles always have opposite spin vector. That's a possibility, at least. And then you can still afterwards decide in which direction you want to measure. So maybe that is the measurement direction at site A, and this here is the measurement direction at site B. No one prescribes anything, but you can be sure that if you are measuring in the same direction, then by this rule that we just said, you will get the opposite result. So applying the rule to B, we would have the outcome at B depending on the measurement direction at B, and we would have the sign of, well, the spin vector at B times the measurement direction, but of course that's just minus the spin vector at A. And so the outcome is exactly that's exactly opposite of what you would get if you were to measure at A along this direction B. Okay. So that means we are guaranteed that whenever the directions are the same, as I just said, then also the outcomes will be opposite, which is very good. So this is obviously just like in quantum mechanics. And so the first test, if you like, of our little toy model, it really passes this test. Then we can go ahead. We can ask, well, but what happens if the directions of the measurement directions are not the same? What happens in particular if I measure in orthogonal directions? So for example, one of them is the Z direction and the other one is the X direction. What happens then? And in order to understand this, it's best to draw the sphere on which all the possible spin vectors can lie, and also draw the two different measurement directions, so the B and the A. And now we have the situation that from the point of view of B, I will get a positive result whenever my spin vector lambda lies on the upper half of this, on the northern hemisphere, so to speak, on the upper half of this sphere. On the other hand, from the point of view of the A measurement, I will get a positive result if my spin vector lambda lies on, so to speak, the right hemisphere, if you call it like this. And now if you look at the combinations of measurement results for both A and B, you will find that among these 4 different sectors that you produce in this way, so there's one sector here, so to speak, and then another sector opposite, and then there's another sector down here and another sector down here. So in total, you have split this sphere in 4 sectors, and they produce all possible combinations of signs for A and B. So plus, 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 minus, minus, plus, and minus, minus. they are all equally large. And if lambda is really uniformly distributed over the sphere, that means they are all equally likely. So A and B have the same sign, so A times B is positive, just as often as they have the opposite sign. I hope this is clear from this little drawing. So if you pick measurement directions at A and B that are perpendicular, the measurement results will be the same as often as they will be opposite. And so that means if you now were to go ahead and calculate the expectation value, the average of A times B, well, then that should be 0. So in order to prepare for what we are going to write down a little bit further below, how would you formally calculate this average? It's an average over the probability distribution. Which probability distribution? Well, the probability distribution of lambda. So lambda is a unit vector, the endpoint being somewhere on the unit sphere. Rho would be the probability density. In the simplest model, it's just uniform. And what do we want to average over? Well, we want to average over the measurement results, and these always depend on the measurement direction and the spin vector. So this is the kind of calculation we would do, but we already know the result. We just graphically saw that positive contributions are as frequent as negative contributions, so the average is 0. That's perfect, that's very fine, because this is exactly also what you would get in quantum mechanics. If you measure in the z direction for one of them and in the x direction for the other one. So if say, for example, in the z direction on one side you find up, then we know that the other spin must be down in the z direction. But a spin that is down in the z direction, when it is measured along the x direction, will equally likely be up or down in this new x direction. So that means the measurement results are uncorrelated. And the same happens here in this little toy model. So when the measurement directions are perpendicular, you get uncorrelated outcomes. And as I just said, this is like in quantum mechanics. Very good. So this little toy model, simple as it is, already has two, so to speak, important points of success. When the measurement directions are parallel, you get anti-correlated results. If they are perpendicular, you have no correlations, just like in quantum mechanics. That's really good. And so it seems at this stage that at least you would have constructed a toy model that can explain the spin version of the EPR Gedanken experiment. And then if that were really true, you would probably move on and try a more physically plausible model. And then you would try to extend this to many other situations. And then eventually, hopefully, you would find the microscopic underlying theory behind quantum mechanics. So that would be the research program. However, there's an important catch. And this is something recognized by Bell. And that was his important new idea. He said, well, let me check what happens if the measurement directions are neither parallel nor perpendicular. And it seems like a little technical step here, but it will actually lead to very important insights. So check other angles between A and B. And now let's see what happens in this particular model. And we will see in a moment that the results will deviate from quantum mechanics. And then we have to make sense of this and ask whether this is only the fault of this particular model or whether it's a more general problem. But let's first look at this model. So again, it is very helpful to draw a picture of this unit sphere on which the lambdas lie. And now we have a situation where A and B are not perpendicular or parallel, but there will be a plane in which both A and B lie. So I'm now drawing a view onto the sphere such that the viewing direction is perpendicular to the plane in which A and B lie. That makes it a little bit easier to draw things. So for example, I could have A pointing directly straight up, and I could have B pointing in some other direction, nothing special. And so now again, I can ask, okay, for A, when do I get a positive result for A? Well, that's obviously the northern hemisphere again. That's when A becomes positive. And then I can ask the same question for B, and I would have a tilted hemisphere. Okay. So that's the hemisphere where B equals +1. And now we want to look at the correlations when we average over all possible lambda. But first, I think there's a question. What happens if lambda is perpendicular to both A and B in the first example? You mean when A and B are parallel? Lambda could be perpendicular. Oh, then it's just on the corner of the decision region, so to speak. I guess it's even a bit ill-defined. You know, we take the sign of lambda times A, and then you could say it's 0, but it doesn't really matter because, as the mathematician would say, if lambda is uniformly distributed over the unit sphere surface, then this is only a single line, so it's a set of measures 0. So you can define it either way. You could say, oh, then the result should be +1, but I don't really care, because it will not affect the any averages that you take. Okay. So again, so this unit sphere represents the location of all possible values that lambda can take. And now I want to do, so to speak, the statistics. I want to find out how often is it, if lambda is distributed uniformly over the sphere, that A and B have the same sign. And so this is now another section. So if you follow it closely, you will find that the area where both A and B are positive is, I have to draw even more complicated things, is this area up here. Nothing else, yeah. So this is where both are positive. And now I have to introduce the angle between A and B, if I like. So that's the angle theta. And you will find this angle theta at several different points in this plot. So you would find the same angle here and also here. And so just to state it, theta is the angle between A and B. Now you can argue A times B is negative, that is, they have the opposite sign. In which section? Or in a fraction of the cases? Well, if they have to have the opposite sign, what I need is exactly these two areas. So it's this little wedge and it's that little wedge. And both of them have an angle theta, actually. So if you look at it from the side, if I draw the situation again, because maybe it has become a little bit cumbersome. If you look at it just straight from the side, this is how it looks like. There's a theta here, and there's a theta there. And so if you think about it for a moment, this wedge as a fraction of the total area of the unit sphere will just be theta by 2 pi, theta divided by the whole angle. And if you take both of these wedges, so this one as well, you get 2 times theta divided by 2 pi. If you don't see it at first sight, maybe you have to think about it again, about the geometry of this case. But this is really the fraction of the unit sphere surface area where A times B would be negative, so where they have different sign. Now, if you believe this little piece of geometry for the moment, then you can calculate what's the average A times B. Because there are only the 2 cases where either the sign is the same or the sign is different. So so we have to be careful now. When the A okay, so when A times B is positive, then of course the result of these measurements should be negative. And this happens in which fraction of the cases? Well, that's just the opposite of what we just said. So it's the rest of all the cases. So it's 1 minus pi, theta over pi. And then it's positive, A times B is positive. Oopsie, sorry. So I just saw I made a little mistake. So A times B is you see when they are parallel, then it's then the measurement results should be negative. If so, because the spin vectors are in the opposite direction. So actually what I wrote down here was the fraction of cases where A times B is positive. So I apologize for that. And that's exactly what we're going to write down. So +1, that is A times B is positive, happens in theta over pi of the cases. So I hope that's clear. Again, if A and B point in exactly the same direction and they're exactly parallel, then the way we construct our spins, which are pointing in opposite directions, we will always get A times B is negative. So if theta equals 0, we should recover just -1. And indeed, this is what happens. If theta equals 0, we only get this first term. We get -1. This is what we said before. Okay, that's great. So now I can just combine these terms, nothing special, just a little bit of algebra. And that would be then 2 times theta over pi -1. Okay, so this is the result for A times B. And now we can plot this. Yeah? So let's just plot this. And we will plot this because later there will be a comparison against what quantum mechanics tells us. But for now, let's just multiply the measurement results at A and B, plot them against the angle between the measurement directions. And what we find is that, well, yes, if they are parallel, we get always -1. If they are perpendicular, we get 0. And then finally, if they are opposite, then of course I get +1. And it's a straight line. This is what this formula tells us. So again, there's a question about this. For A times B, So if theta equals 0, A times B will always be negative. This is what we said before. And the reason is that one of the spin vectors is lambda, but the other one is minus lambda. And for that same reason, if I want A times B to be positive, I have to be in one of these little wedges. So either here or there. So these are the little wedges that would vanish if theta equals 0, but which grow if you grow towards theta non-zero. So this is correct. So the way it's written down now is actually correct. And this formula down here is then actually consistent with the slope here. Okay, I hope that's clear. No, very good. That's the result of this toy model. The only cases that we tested against quantum mechanics so far are this one and that one. And we could also have tested that one here, and that is also correct. The question is whether we have quantum mechanics agreeing with our little toy model also elsewhere. There's another question, shouldn't you get always +1 if theta is 0? No, again, the reason is this: if A and B point in exactly the same direction, the point is that the lambdas on the different spins still point in opposite direction. This is how we defined our model. And that's why I get a negative result if A and B are, a negative result for the correlator if A and B are parallel. So do you now understand why I get actually -1 when theta equals 0? Theta equals 0, meaning that A and B are exactly the same vector, pointing in exactly the same direction. Okay, good, very good. Yeah, so it's you can easily get confused with science, as I was apparently in the beginning. Okay, good. Now what about quantum mechanics? Let's ask, what about quantum mechanics? For arbitrary angles. So let's do the same calculation in quantum mechanics for the singlet state. And this is something where I will not go through all of the calculation, but I will just show you what you would have to calculate. So first of all, it's an expectation value in quantum mechanics. The averaging is done as an expectation value over the pure state that you try to measure, so the singlet state, psi. And then the measurement result of the spin in an arbitrary direction, we discussed that briefly, so you can project the spin operator on this arbitrary direction. So you would take the spin operator representing spin, let's say 1 on the left side, with a measurement direction A on the left side. And you would do the same for the right side, so direction B times sigma 2. And you take the sigma vector, because again, I remind you that is always a vector that contains the Pauli matrix operators for the spin, whose eigenvalues are plus or minus 1, instead of say plus or minus h bar half, as you would have for the spin operator S. And so that's perfect, because then the outcomes will be also plus minus 1, exactly what we need. Okay. And now you can actually evaluate this, and this would be a little homework exercise. It's easiest if you choose your coordinate system so that, say, one of the two vectors, like A or so, it looks very simple, 0, 0, 1, and then you only need to care about B, and that will be enough. But the outcome will be, in any case, if you carefully do your calculation, simply the scalar product, or minus the scalar product of A and B. And so since theta is the angle between them, this is just minus cosine theta. Okay, so that's just the outcome of an honest quantum mechanical calculation. And we see that it's completely coinciding with our toy model result at theta equals 0. So that's nice, I get -1. At theta equals pi half, I get 0. And at theta equals pi, I get +1. So that's perfect. But in between it's simply very different. Yeah? In between, well, I have this cosine. Maybe it doesn't look quite symmetric the way I drew it, but that's supposed to be a cosine, and that's the result of quantum mechanics. Whereas this line is the result of our little toy model. So that's, so to speak, a disappointment. If you already hoped that your little toy model would produce the correct outcomes that quantum mechanics predicts. And so at least we have to conclude that at least within this toy model, where we were able to produce the perfect correlations, we do fail for intermediate angles, and we don't even get to quite the level of correlations that quantum mechanics predicts. So aside from these extreme cases, there's clearly a gap, an important gap between quantum mechanics, which predicts higher correlations, and our model, which predicts lower correlations. So we can't reproduce the amount of correlations that quantum mechanics predicts. Now, at this stage, immediately, one objects and says, well, okay, this was a particularly simple model. We didn't even have a good physical justification for it. We took the first thing that came into our mind. So maybe there are other models there. And I don't know what happened historically. Maybe Bell really did try for some time figuring out other models, and then he failed with model after model. So what happens actually is you can make some models that maybe look a little bit closer to the quantum mechanical curve, but then they don't reproduce the perfect correlations. So they will produce values a little bit below at the extreme cases and so on. So you can wiggle a little bit, but you can never quite make it work. And then after a while, at least, apparently he asked himself the question, is this a general rule? Is it always true that we cannot quite reproduce the quantum mechanical correlations? So that's the question we want to answer now. And in order to answer this question, of course, we have to be, well, if we want to ask, is this a general problem? Then obviously we have to generalize away from our model. We have to consider a whole class of models that are somewhat similar to what we are saying here, but not nearly as specific. We don't want to be talking about spin vectors and unit spheres and equal distribution of a vector on a unit sphere and all these ingredients. So we want to be much, much more general. We want to be as general as possible while still being able to make some predictions. And so this is now the great achievement of John Bell, to have realized that there is some general rule to be discovered here. So what we will now do to set up Bell's inequalities, we first define the generalization of this kind of model. And you already know from our previous discussion that we would call such a model a hidden variable model, because it introduces extra variables, like here the spin direction, that are not present in the quantum mechanical description, but to which we ascribe some sort of reality and which we will then use to predict the results of measurements and so on. So we would say we have here a hidden variable model. And there's one very important aspect, and that's also the genius of Bell, to have realized that this is a very important ingredient. It's a so-called, what we now call a local hidden variable model. So the local is very important. And I say in a moment what that means. Just let me say that sometimes we use the abbreviation LHV for the local hidden variable models. So what we will now do is not try to define a general local hidden variable model for any situation in quantum physics. That would be even more ambitious. But just what is the general local hidden variable model for the purposes of this spin version of the EPR experiment. So that makes it a little bit more concrete. In particular, it will mean that we know what the measurements should give us. The measurements, so there are two particles or two stations. At each of them, a measurement can be made. The measurement can only be plus or minus 1. So there will be measurement results at both sides. And we would call them A and B, and they can only be plus 1 or minus 1. Now, what do they depend on? Well, again, here, I want to say the measurement result at A, it should surely depend on the measurement direction I choose, because that's a feature of the whole physical setting. In the end, in the quantum physical description, I'm trying to measure a spin, so there is a measurement direction A. Okay, so that's a kind of unit vector. And then borrowing from our special toy model, we would say, well, it depends on the measurement direction, but it also depends on somehow the properties of this particle, the hidden properties, the extra properties. In our case, that was the unit spin vector lambda. But I will now say more generally, it depends on some lambda, whatever it might be, a unit vector, a tensor, a field, something magic, some kind of lambda. And the same goes for B. So this lambda now becomes our hidden variable. And I said before, this does not need to be a single vector or a single scalar value. It could be a vector, could be even a full field, any object you can possibly think of, a matrix or whatever. Yeah. And then there's one other important ingredient that we want to generalize, namely this hidden variable, though it is given for each individual experimental run, overall, between different runs, it will be chosen at random. And because it's chosen at random, there is then a probability distribution. And we would call that rho of lambda. So it lives on the space on which lambda lives, whether lambda be a scalar or a vector or something like that. Now I want to come back. So little a and little b are obviously the measurement directions. This I already said. I just should write it down as well. Now I want to come back to the question, why do we call this local? So what is it about this very general looking mathematical setup that tells us that we have a local hidden variable theory? Well, it's local because what we don't allow is that the measurement result at A also depends on the measurement direction at B. So this is the one thing that we don't allow. This is, we don't want to be as general as that. Yeah? And it's local because it makes sense that if interactions are local and if light signals didn't have even the time to travel to the other measurement station, then what I set at B cannot influence the result at A. At least that was even the original reasoning in the logic of EPR. So we call our model local because we explicitly don't allow this influence. Okay, so that's very important. Yeah? This is the most important point of everything. If we did allow that, anything could be possible. If we don't allow that, severe restrictions will follow and Bell's inequalities will follow. Okay, and so that defines our general local hidden variable model for this particular Gedanken experiment. And our goal will now be, again, just as before, but more generally, to derive any constraints we might have for the statistics. We can obviously not now directly calculate in general the correlator of A and B, because it will depend on the probability density rho and on the functions A and B. But maybe we can still derive some constraints. Okay, so that will be the goal. Is this setting clear so far? It seems so. So I will just go on, but please stop me if something becomes unclear. So again, the statistics, that's always just the product of the measurement results averaged over all the possible values of lambda, because this is averaging over all the possible different experimental runs. And so I just write down again what I wrote before. Sometimes I will also call this the expectation value that depends on little a and little b. Okay, and we already have a little bit of a feeling from our special toy model that it might be smart to look at different combinations of settings, not only when A and B are parallel or perpendicular, but maybe also intermediate angles. So this we learned from the special toy model. And if one does this for a while, I already mentioned that in principle one can have compromises. So in principle one can build models that are pushed up a little bit here, but at the expense of being pushed down at the other end. So it will not be smart only to look at the value of this correlator at a particular angle, but we should look at it, so to speak, at multiple angles simultaneously and describe this kind of compromise that has to be made. Okay, so now I will first, so there are different versions now of this argument, and I will first, however, really go through what Bell originally proposed, and then we can generalize it a little bit. So it turns out it's enough if at each of the measurement stations we consider two different directions. So this is now really how Bell did it. So we will have a little a and a little a prime. These are two different directions. And we will also have a little b and a little b prime. Again, two different directions. And sometimes I get a little bit tired of writing. So we will say things like the measurement result at station A for the setting A prime, I will just abbreviate as capital A prime. But it's understood that this is, it's fluctuating because lambda fluctuates, and it is belonging to the particular measurement direction A prime. Okay. So now we want to make our life even a little bit simpler. We could say the following. If A prime is actually equal to B prime, so they are parallel, and if we get results that are compatible with quantum mechanics in this case, then we should observe perfect anticorrelations. So we would have A prime equals minus B prime, and that would be true regardless of which value of lambda you choose. Yeah? Otherwise, you would be in conflict with quantum mechanics. There's a little caveat, strictly speaking, since we're talking about probabilities, you could afford, if this equality was violated, at a set of measure 0, because it doesn't contribute to anything and will never be observed, so to speak. It never happens. It has probability 0. That's what that means. But these are details. So now we just say A prime equals minus B prime for all lambda. Okay, fine. And now let's do a very simple 3-line calculation, which is the kind of calculation that Bell did originally back then. And we will then find a very remarkable constraint on what can happen to this correlator. So 3 lines, basically. You first don't even consider the correlators, which is always the averages of A times B and A times B prime and so on. Let's just consider the individual numbers. So when I now write down something like this, what I mean is for a particular value of lambda. So each of these A's and B's and B primes are for a particular value of lambda. That's important. Okay, so now I can consider this combination of terms. Again, A and B prime are all plus or minus 1. So here I subtract 2 terms that are either plus or minus 1. This is all that can happen here. Now, well, the first very, very trivial thing is you can pull out the A and put it in front of both. So that's obviously correct. The next obviously correct step is that since A is just plus or minus 1, the magnitude of A is 1, so you could say this. That's obviously correct. And now at some point, I want to bring in my knowledge of these perfect anticorrelations. So I will now use that we just said B prime is always minus A prime because we chose the directions parallel. Okay, so I can write, yeah, I could write it like this, minus A prime minus B, which is of course the same as A prime plus B, because it's below the magnitude. And now a final trick that is nice. In principle, that would be the end of the calculation if A and B are arbitrary numbers, but we already know they can only be plus or minus 1. So I claim that because of that, I can also rewrite it in another fashion. And I claim this is always possible because they're both just plus or minus 1. The easiest way to check this is actually to go through all the 4 combinations and convince yourself that this is correct. For example, if both are 1, then 1 plus 1 is 2 in the upper part, and equally in the lower part I get 1 plus 1, and you go through all the other combinations as well. Okay, so that's obviously true. These are all on their own very, very trivial manipulations. You still ask, okay, where does that, what do I gain from this? And now is the point when we really want to do expectation values, because in the end we want to be talking about correlators and learn something about those. Now, let me try to take the expectation value both on the left-hand side of this equation, which is the one up here, and then also on the right-hand side. Taking the expectation value on the right-hand side, that's straightforward. It's just 1 plus the expectation value of A prime times B, so that's clear. But on the left-hand side, what that means, we have the expectation value of something that is inside a magnitude. Let me call it X. Yeah? Now, that's not so convenient, you see, because in the end, I'm interested in writing everything in terms of correlators. So something like expectation value of A times B prime. However, unfortunately, that's sitting inside the magnitude. So somehow I want to get these averaging expectation value brackets, I want to get them inside the magnitude. Now this I cannot do via an equality, but I can do it via an inequality. So the following is certainly true. If I first take the magnitude and then average, I always get something that is probably larger than if I first average and then do the magnitude. And why is that? Well, that is simply because X might be positive and negative. So if I do the average first, then the positive and negative parts might cancel each other, partially at least. And then I take the magnitude and I get a small number. Whereas if I first take the magnitude, all the negative signs go away. And then I average, then of course I get something larger in general. So this is at least a correct mathematical inequality. And so now if I take the expectation value on the left-hand side, the one written up here, and apply this inequality, then I can really pull the expectation value inside. And now if you think about it, since the expectation value inside is less than the other version, I really have less or equal than the rest. And on the right-hand side, I already said it's trivial. Okay. So I hope you could follow. These were a few simple manipulations, ending up with an inequality that constrains our correlators. They cannot be arbitrary. Even though our model is quite arbitrary, these correlators cannot be completely arbitrary. And this is really what Bell derived in 1964. Yeah. So that's the famous first version of the Bell inequality. Again, in principle, the mathematics itself is quite trivial, but the consequences, conceptual consequences, are very far-reaching. But first I want to ask, before we discuss the conceptual consequences and so on, and look at how we could generalize it and so on, are there maybe straightforward questions here about the derivation, about these few lines? That doesn't seem to be the case. You have to understand that people now, of course, once you know which game you want to play, then you can quickly generalize this to many other settings, and we will go through such a generalization. There's one question already. Can you explain again what is A prime and B prime? Oh, that is just, for example, A prime is simply the result A at station A, but now for the particular measurement direction, little a prime. So this is just the attempt to bring into the game multiple possible measurement directions. And why are we making this attempt? Well, because earlier on we explained that you might also want to look at different angles and not just parallel orientation of the measurements. Or simply A prime, capital A prime is simply the result at station A in case you measure along the direction little a prime. That's all. Okay, and so you see now this is comparing different correlators that would be obtained in different experiments. So for example, this is one where the measurement directions are little a and little b prime. This one here has little a and little b. This one here has little a prime and little b. So different combinations of measurement directions. And if you were to do all these experiments, then in case you have this underlying local hidden variable model, the correlators must fulfill this inequality. Okay, so this is obeyed by really every local hidden variable model under the condition that we introduced earlier, that it show perfect anticorrelations in case you have parallel measurement directions. So that coincides with quantum mechanics, at least in this particular case. Okay. So this in itself is nice to know, but the important conceptual meaning comes out only once you start comparing with quantum mechanics or with experiments. But of course, at the time, no experiments existed. And so one had to compare against quantum mechanical theory. And that's what we are going to do next. So the question would be, if I calculate the results for quantum mechanics for particular angles between the measurement directions, will they fulfill this inequality? In which case, at least there would still be a chance that a local hidden variable theory can explain quantum mechanics. If quantum mechanics violates this inequality, then there is no chance, because then there would be a contradiction. Okay, but first let's look at it. So we already know that for quantum mechanics, the outcome is simply the scalar product or the negative scalar product between the two measurement directions. And now it is up to us to choose interesting measurement directions. And we could certainly choose them in a not so smart way. Not so smart would mean that well, the quantum mechanical results do fulfill this inequality. There's no contradiction, at least for these measurement directions. And then maybe we would go home and not have learned anything. So just as before it was Bell's smart idea in the toy model to look not only at 0° and 90° angle between the measurement directions, but at arbitrary angles. Also here, the choice is very important, which directions you want to look at. And so here's one particular choice that Bell proposed. I draw 4 vectors for A, B, A prime, and B prime. They are not chosen in a very difficult manner. A and B are perpendicular, and A prime, B prime are parallel to each other, as we supposed actually in our argument, and they are 45° with respect to the B axis. Okay, fine. So now we can calculate the scalar product. It's not very difficult. And we can calculate what are the predictions of quantum mechanics. So for example, A and B prime, they have a 45° angle. So the scalar product is 1/√2. And then according to this formula, the quantum mechanical result is minus 1/√2. Okay, fine. Then A times B, according to quantum mechanics, well, they are perpendicular, so they come out 0. That's fine. And then finally, A prime B, that's the other combination we will need, is again minus 1/√2. So not very complicated. Now, we can calculate, we have a look again at what we need to calculate. We will need to calculate both the left-hand side and the right-hand side and see what happens. The left-hand side, we need the correlators AB prime and AB. So AB prime and AB. Well, one of them is minus 1/√2, the other is 0 anyway. So what I get is 1/√2, fine. And on the right-hand side, I have 1 plus A prime B. And that is 1 minus 1/√2. Okay, so far so good. Now, according to Bell's inequalities, the left-hand side should be less than or equal to the right-hand side. So let's see what happens. The left-hand side is 1/√2. The right-hand side is 1 minus 1/√2. And it's simply not true that the left-hand side is less than or equal than the right-hand side. You can work it out for yourself. For example, you can multiply all sides with square root of 2, and then you will find that 1 is not less or equal than square root of 2 minus 1, because square root of 2 minus 1 is approximately 0.4 or so, which is not larger than 1. Yeah. So the important observation is that, at least for particular angles, quantum mechanics, or the quantum mechanical results for this particular Gedankenexperiment, violate the Bell inequality. And so that now has an extremely important consequence, because it means no matter what you try, no matter how smart you are in adjusting your local hidden variable model, you will never make it coincide in all the cases, which would include these angles, with quantum mechanics. So mathematically speaking, you could say there exists no local hidden variable model that is compatible with quantum mechanics for all the possible angles. Again, there is this little caveat that we considered explicitly local hidden variable models that try to have perfect anticorrelations if the measurement directions are parallel to each other, but they should have that anyway, because otherwise they would also violate quantum mechanics. So this is very, very, very important. Yeah? Well, it's hard to overstate the importance of this. It's very rare in physics that instead of, say, proposing one particular model or ruling out a very special model, we can rule out a complete class of potential models that sound very reasonable. And I would contend that these local hidden variable models are very reasonable from in point of view of their logic. So this is the deep conceptual meaning of Bell's inequalities. Suddenly, you find that quantum mechanics cannot be matched by any of a large, large class of reasonable models, all these local hidden variable models. Now, it could, of course, be that quantum mechanics also doesn't describe nature, and then this would still not be any statement about nature. But if you are then able to produce experimental situations where the quantum mechanical predictions are fulfilled, and that would also, however, have to obey Bell's inequalities, then there is a contradiction not only between local hidden variables and quantum theory, but also between local hidden variables and experimental results. So local hidden variables would contradict nature. That's the meaning. So I want to pause here again. We will generalize this and tie up a few loose ends here and there, and then say something about experiments and so on. So this is all interesting, but it's very important that you understand the impact here. And this is the impact that I tried to explain already when discussing this Mermin illustration of the Gedankenexperiment initially, because I didn't even make reference to quantum theory and still explain to you that there doesn't seem a reasonable theory, a reasonable model that could explain the observed correlations. Aha, good question. Is the case in which the two particles are continuously interacting excluded by Bell's inequalities? Yeah, I would say this case is excluded by the setup. We want to have a situation where locality is guaranteed, and locality for us has a very specific meaning. It means the measurement result at one station cannot depend on the measurement setting on the other station. Now, if the particles are still close enough apart that they can influence each other via interactions, then this would no longer be true, because you set the measurement direction at B, maybe a magnetic field direction, that would somehow change the motion of the particle at B. And if it still interacts with the particle at A, then of course some information about the measurement direction B could be transmitted to the other particle. And then we could not start from this ansatz. Yeah. So in any experiment, you must make sure that they are no longer continuously interacting, typically by having a large distance. Now, that being said, if you can actually have them interacting if you make a measurement that is sufficiently fast so that not even a light signal could travel, under the assumption that you of course have to make that these interactions also cannot travel faster than light, which is true for all the physical interactions we tested. Okay, then can you again explain the meaning of the hidden variable lambda? Well, so this, you understand at least the meaning of lambda in this particular version of the toy model. There it was, so to speak, the real spin vector. Maybe you don't observe it all the time. And in a measurement, it's somehow discretized and only leads to measurement results up or down, depending on how it's oriented with respect to the measurement axis. But it's already there before. So it's exactly the kind of thinking you would have for a classical model, where you would talk about a particle that rotates and maybe has some internal vibrations and so on. And so you need multiple variables to describe all these internal degrees of freedom, everything that goes on inside this particle. And even if you can't measure all of these, maybe, that could happen even in a classical model, maybe you don't have the measurement apparatus, even if you can't measure them, they're all real still at the same time, and they can all influence somehow the results of a measurement. So that's how you should think of this lambda. Now that's of course a very special model, and you might say, okay, I don't buy this special model with this funny spin vector that's taking these cartoons a little bit too literal, but the purpose of defining this general local hidden variable model is that it's a whole class of models, and the lambda could really be anything. The lambda could be a magic, mysterious wave field that no one has yet discovered, but on which the results of this measurement depend, for example. So lambda can be really infinite dimensional even. And so the beauty of Bell's inequality is that regardless of how complicated you allow yourself to construct your local hidden variable model, you will not succeed. This is the outcome, the statement of Bell. And that's of course super important, because otherwise maybe we would have had several generations of physicists wasting their time in trying to construct such models, which simply don't work. That's a little bit like ruling out a perpetuum mobile. Okay, so many more questions. Mathematically, the argument is also based on the assumption that whatever lambda is, we can always assign a probabilistic distribution to it. Is this always physically justified? It's true. We assume this is part of the description of this local hidden variable theories. We have to be able to assign a probability density to lambda. If someone comes up with a model outside this realm of models, then of course the discussion starts again, but it's a little bit hard to see. If you start trying to construct something, it will not be so easy, you see, to get around this. Yeah, so this lambda could also, in principle also have memory effects and all kinds of stuff built in it. It would still work. Okay, next question. If we exclude locality, obtaining global hidden variables. Yeah, so if we go away from this set of model, obtaining global hidden variables, could there be any physical justification for this, except some kind of superluminal interaction, which has its own problems? Well, I don't see it. I think that anything where you claim that changing the setting at the other detector can influence your measurement at the detector A, beyond the speed of light, so to speak, that involves some superluminal action at a distance. So I don't think that you can say, oh, I don't like the local, but I also don't like the superluminal. Okay, then next, spin singlet is related to wave function antisymmetrization. Well, yes, that's right. So in a matter-Pauli principle, if particles are far apart, what physically preserves the spin singlet structure? Very good question. Nothing particularly preserves it, but also, well, but also nothing kills it usually. So what you want to make sure is, of course, to preserve the singlet structure. What would be terrible is if, for example, the spin traveling to the right would go through some random magnetic fields that give it some random extra precession. And then maybe in each run of the experiment, you get a different random precession. Then you would destroy your singlet state. That would be bad. So there's nothing that actively keeps the particles in the singlet state, but unless you somehow act on the spins, like with random extra magnetic fields, it will remain simply in a spin singlet. And I should also add that, yes, since you mentioned Pauli principle, so the easiest way to obtain such a spin singlet wave function is, of course, if you have, say, electrons that are, with respect to the orbital wave function, in a symmetric state, and then because of the Pauli principle, the spin part has to be antisymmetric, so it has to be the singlet. So that's the easiest way. However, you could also have, say, bosons, and just by very careful preparation, have some overall wave function where the orbital part already is antisymmetric, and then the spin part is also antisymmetric, and overall it's still a symmetric wave function as is required for bosons. And you can also have other more abstract systems that are not even really spin 1/2 and not single electrons, rather some funny qubits that you constructed on larger scales. And you have enough control over them, you can produce such a singlet state. Okay, here's another comment, probably going back to the particles that are interacting. The picture you have in mind is two particles that are continuously interacting. In that case, they can be as far as much as we want, but their states correlate by their continuous interaction. The result of the measurement is defined a priori, and we are just describing something that was already there. Is this picture excluded? Well, the problem is that all the interactions that we know, including, say, Coulomb interaction, they only propagate at the speed of light. So if you choose your measurement settings only at the very last moment, then there is simply no time for this information to propagate to the other particle, even via the always present interaction. So that's the thing that would be still missing. Yeah? So because if suddenly something changes, like a magnetic field direction or so at the spin B, then of course, yes, the electron could get a sudden acceleration or something. But in order for this to be felt at the other measurement station, there would be an electromagnetic wave traveling to the other measurement station. But if it arrives only after that measurement has already concluded, then it will have no influence. So that's the idea. Okay, I am asked to summarize again all the hypotheses behind Bell's derivation. So let's go back. There are not many. There's just this setting that, first of all, we're talking about a situation where we somehow do have two particles or two stations or something distinguished by A and B. Then there are measurement results that can only be -1 or +1. These measurement results depend on the measurement direction, but only at the particular detector, so either A or B. And they can also be made to depend on some unspecified magic hidden variable, lambda, about which we know nothing, except that in repeated experimental runs, it's basically random and again drawn from a new, from some given random distribution. Well, we already said that it's local. And then for the particular derivation that we discussed here, we also wanted that if you are having parallel measurement directions, then the results are automatically anti-correlated, which is the result demanded by quantum mechanics. And that is it. From there on, it's just mathematics. And then you have to see whether that mathematical outcome is something astonishing or not. And as we remarked, it is quite astonishing because at least it is not compatible anymore with quantum mechanical results. And so we already know that all the local hidden variables models that we so defined cannot match quantum mechanics. Oh, there is a question. So in the end, the real constraint is that the measurement system affects the result. I mean, the constraint for local theory to be valid. So I guess the Bell's inequalities are not making any statement as to what exactly is the extra magic that goes into quantum mechanics that is responsible for the deviations from the local hidden variable model. So you could then speculate, of course, what happens, but you know that even in this setting, even here, it's not excluded that the measurement apparatus, even in this kind of model, heavily influences the system and, for example, completely scrambles the internal lambda when the measurement is made or anything like that. That is all in principle part of this game. The only thing that isn't excluded explicitly is that you cannot be sensitive to the other measurement setting. I hope I have explained all the questions. Is there some question I missed? Okay, doesn't seem to be the case. So, there's still some question. Yeah, thank you for reminding me of something. So when we go back to this Mermin version of the, setting, and we will come back to linking this to Bell's inequalities in a few, maybe beginning of next time. But you recognize, of course, the setting. And then what we concluded was that we would think that there is some predetermined properties, which we now would call lambda, and that we could summarize them, so to speak, in a little table. And this table basically would give us this function that maps, or this table would be specifying a particular lambda and what would be the measurement results in the different measurement setting directions for this particular lambda. So the choice of table is like a choice of lambda. Maybe you choose it randomly. And then for each particular lambda, there's a very specific table that tells you what will be the outcomes. Are we excluding full determinism? Well, no, I would say so. Full determinism probably would mean that even lambda is not random, but this is just a special case of a probability density that is peaked at a particular value of lambda, if you like that. Okay, so we still have a few minutes. I want to go through a little generalization that is quite famous. And at least let me go through the mathematical derivation and then we can discuss its meaning next time. And so this is a generalization from a few years later that removes some of the special constraints that we needed in the derivation of Bell. And And so this generalization is from 1969, and it's a paper of 4 people, Clauser-Holt-Horne and Shimony. Now, they were able to get rid of several constraints. So first of all, in any realistic measurement, it can easily happen that the particles get lost on their way to the detector. So instead of getting a result +1 or -1, you don't get any result. So what they did to cover this case is that all these random variables, A, B, A prime, B prime, cannot only take the value -1 and +1, but also 0. And that you could assign whenever you don't have a detection event, simply because some particles got missing, which is very easy to happen, say, for photons. Also, we do not want to assume something special about the measurement directions and something like, what did we have? A prime equals -B prime or anything of that sort. So no assumptions in this regard. So A, B, A prime, B prime can correspond to completely arbitrary measurement directions. And so now they went through an exercise rather similar to Bell. And again, we know a little bit of the trick by now. So you always consider these products of A, B, A prime, B prime, and so on. You consider some combination of them. Maybe sometimes you take a magnitude of those. And then and you derive some equality or inequality. And then you take also expectation values to lift this to the level of correlators. So now I don't know how long they had to try around for this to work, but in the end, it's not so difficult, at least to follow that it's correct. So here's the combination that they eventually considered. Okay, you see AB plus AB prime and A prime B minus A prime B prime. Now, it's clear that in the first case, I could again take A times B plus B prime. This is like what we did before. And now if A were +or -1 and I take the magnitude, it's always 1, so it's trivial. So I could just say, just like before, the whole thing is equal to the magnitude of B plus B prime, so the A would drop out. Now, however, A can also be 0. And these cases, of course, make the overall value smaller, yeah, because 0 then multiplies B plus B prime. So what I can still say, this is less or equal than the magnitude of B plus B prime because of these extra cases when A is 0. Plus, for the second part, I can do the same. I pull out A prime. A prime can also be 0. So again, inequality. Okay, so that looks very nice. And then I can claim the following. If you now go through all the possible cases of these variables, B and B prime can be -1, 0, or +1 each of them. Then you will find that the largest value that you can possibly have for the sum that sits here is 2. Can never be beyond that. And you can check this very easily. For example, if both B and B prime are 1, then the first term will be 2 and the second will be 0. And then I can have the opposite. And also I can have one of them being 0, but then again, I do not surpass 2. So it's very simple, actually. And now I use my old friend, this inequality that tells me that taking the magnitude first gives me larger results than taking the average first. And so if I now take the expectation value on both sides of the equation, I will arrive at the following inequality. So starting from the top, I have now magnitude of AB plus AB prime plus magnitude of A prime B minus A prime B prime correlator. And all of that corresponds to this side of this inequality. So it's less or equal than the rest. And we already had a less or equal, which is very fine because otherwise I would run into trouble. So this chain of inequalities always has to have the same direction of the inequality. But so this is less or equal than a whole sequence of steps, and eventually, therefore, less or equal than 2. So this is the famous Clauser-Holt-Horne-Shimony inequality. And this is what is used primarily in modern experiments. So conceptually, it is a Bell inequality. It's just a slightly more generalized version. And so you see, these are just mathematically just a few lines, and we will discuss their full impact next time. But it's just mathematically, it's just a very simple game. You have 4 random variables. They can be -1, +1, or 0. You arrange them in some fashion. You take some combination and expectation values, and voila, you have this inequality. Nothing super deep there. But the genius of Bell, of course, was to realize that such a simple manipulation could give you such a big insight into quantum mechanics and eventually nature. Okay. So this is certainly something we will discuss again next time. And say again where locality here enters. It's a little bit hidden. But that's formally the CHHS inequality. Okay, any questions at this point? I don't see any at the moment. Okay, someone doubts the triangle inequality that we are using. So you're saying this one. So what is it? Oh, okay, so the question is, this might not be satisfied for some spaces, but remember, I'm not doing anything fancy. This X here is not an arbitrary vector, something, and even more fancy object, and then I would have to tell you exactly how what's the metric and anything. This X just stands for a simple number. It's not even complex or anything. It's just stands for these numbers A, B, A prime, B prime, which are just -1, 0, +1. So I'm doing something very simple. That's the idea. And the average is, of course, the average over all possible values of lambda, but that doesn't present a problem. Okay, any more questions here?